Imagine building like a revolutionary trillion-dollar high-speed rail network across the entire globe.
Right. Massive undertaking.
Exactly. You're laying down thousands of miles of this magnificent track, but you only build 10% of the train stations needed to actually let the passengers off.
That would be a logistical nightmare.
I mean, you'd have these incredibly fast trains just endlessly circling the Earth because there's quite literally nowhere for them to dock.
Nowhere to actually deliver the payload.
Exactly. And that massive kind of glaring oversight is exactly what is happening in the modern space industry right now. So welcome to today's deep dive.
It's great to be here.
Our mission today for you listening is to take a highly concentrated analytical note we received. It's titled Eingefickter Text, and really unpack a completely invisible bottleneck that is holding back the future of global communications.
It forces a massive shift in perspective, honestly, because, we are so conditioned to look up.
Always looking at the sky, yeah.
Right. We track the lowering costs of launching payloads. We look at the massive deployment of satellites in low Earth orbit, the proliferation of orbital lasers.
All the flashy stuff.
Exactly, the flashy stuff. But the source material here, it pulls our attention violently back down to the dirt. It reveals a critical terrestrial problem, which is the physical optical ground infrastructure.
Because you have to actually receive the data down here.
Yes. The space segment is maturing rapidly, but the ground segment, to actually catch all that data, it's lagging behind by an order of magnitude.
Okay, let's unpack this. The sources we're looking at outline a high-stakes engineering deficit, the specific companies racing to plug the gap, and a pretty sobering reality check on the actual capital flowing into the sector.
Yeah, the financial reality is a bit different from the hype.
Big time. And to really grasp the market opportunities here, you have to understand the sheer scale of the dysfunction. The number that jumps right out of the analysis is that the industry has only built roughly 10% of the required optical ground infrastructure.
What's fascinating here is that 10% figure, it is the hard cap on the entire orbital laser communications market.
Wait, really? The whole market?
The whole market. I mean, it doesn't matter if you have a constellation of 1,000 satellites equipped with state-of-the-art optical inter-satellite links.
Right.
If they are generating, terabytes of data over the Pacific Ocean, and there is no optical ground station in their line of sight to downlink to, well, that data is trapped in orbit.
Just stuck up there circling like the high-speed trains.
Exactly like your train analogy. The space innovation is vastly outpacing Earth's capacity to actually catch what those lasers are throwing.
And the note takes this a step further, right? It elevates this from just a tech headache for some Silicon Valley startup to a national level vulnerability.
It does. It gets into the geopolitics.
Yeah, it explicitly states that this infrastructure deficit is a direct threat to a major White House policy objective, specifically mentioning the Golden Dome initiative. And, just to be clear for you listening, we're not endorsing or taking any political sides on the Golden Dome policy itself. We're just impartially imparting what the analysis is telling us here.
Right. Our job is just to report the findings in the note.
Exactly. But how does a lack of ground receivers threaten a White House policy?
Well, the connection there is all about the strategic reliance on secure, high-capacity, instantaneous data transfer.
Okay.
Whether you are looking at defense architecture, secure financial networks, or advanced sensor data, the Golden Dome policy relies fundamentally on data reaching the ground without interception or delay.
Which is why they want lasers instead of radio waves, right?
Exactly. Optical communications are highly desirable for this because laser beams are incredibly narrow. They are very, very difficult to jam or intercept compared to like a wide beam radio frequency that just broadcasts everywhere.
Right, a radio wave just spills out in all directions. A laser is a tight beam.
Precisely. But if the ground mesh isn't physically there to receive that secure laser downlink, the policy cannot be executed. The data architecture fails at the literal last mile.
Wait, I need to push back here before we go further into the companies trying to solve this, because if SpaceX is launching the vast majority of these low Earth orbit satellites...
What if they are?
Right, and they're building their own massive Starlink constellation, why wouldn't they just build out their own proprietary ground stations and monopolize the whole thing? Like, why is this 10% deficit such an open market problem for other companies?
It's a great question, and SpaceX absolutely drives the ecosystem. The source actually acknowledges that SpaceX wins by default in many ways.
Because they just have so much volume.
Yes, their sheer volume forces the maturation of the entire optical supply chain. But building a globally distributed optical ground mesh requires acquiring real estate. It requires securing zoning permits and laying high-capacity fiber optic interconnects across dozens of sovereign territory.
Oh, wow. Yeah, I didn't think about the international real estate part.
It is a geopolitical and logistical nightmare. A closed proprietary system from a single company, even one as big as SpaceX, just isn't enough to service the entire global commercial and governmental demand. The ecosystem requires specialized third-party infrastructure.
Which brings us directly to the money. Because whenever you have a bottleneck that threatens major governmental policy and hard caps a trillion-dollar industry, solving that bottleneck becomes highly lucrative.
Always follow the money.
Here's where it gets really interesting, because the source note maps out the capital flows, and there's a fascinating division between the short-term band-aids and the long-term structural plays.
Capital generally flows toward the path of least resistance to keep the system functioning today, while simultaneously funding the ultimate architectural solution for tomorrow.
Right, so let's look at the near-term cash first. The analysis explicitly states that immediate capital flows are going to what they call relay providers.
Yes, the Band-Aid fix.
Right. And the specific players listed are Kepler, Space Compass, which the note mentions is actually a joint venture between NTT and the satellite operator SKY, perfect JSAT, the tickers there, NTTYY and SKPJAF.
Yep.
And it also mentions General Atomics. So how exactly are these relay providers acting as the Band-Aid for the missing ground stations?
Well, they're essentially building detour routes in space.
Turos.
Yeah. Since we lack the ground stations, let's say a satellite collecting data over an unserviced region like the middle of the ocean, it cannot beam it straight down. There's no station.
The data is trapped.
Exactly. So instead, it fires its laser sideways to a relay satellite in a higher or different orbit.
Oh, I see.
That relay satellite then bounces the data along an orbital chain, satellite to satellite, until it finally reaches a node that happens to have a line of sight to one of the few functioning optical ground stations on Earth.
So they're keeping the data moving in orbit rather than letting it sit on a satellite just waiting for the Earth to rotate beneath it.
Exactly. It's an active workaround.
But that has to introduce significant latency, right? I mean, every time you bounce a signal across thousands of miles of space to another satellite, you are adding milliseconds or more to the round trip.
That latency cost is exactly why relay providers are categorized as the near-term solution.
Ah, okay.
Bouncing signals through an orbital mesh works perfectly fine for bulk data transfer. But if you are dealing with high-frequency trading networks or real-time military targeting data, you cannot afford the latency of multiple orbital hops.
Every millisecond matters there.
Exactly. The most efficient, lowest latency architecture requires the satellite to beam the data straight down to Earth the absolute moment it is generated.
Which means you need the other 90% of those ground stations built.
Precisely.
And that's where the source pivots to the long-term structural winners, which are the photonics hardware manufacturers.
What one's doing the heavy lifting?
Right, the companies building the actual physical stations and the complex terminals inside them. We are talking about Cailabs, Safran, ticker SAFRY, which manufactures the optical ground stations, and another public company, SGBAF, that works with Cailabs for terrestrial optical terminals.
The barrier to entry for manufacturing these stations is just immense, which is why a select few hardware companies stand to be the structural winners here.
It's not just a standard dish, I'm guessing?
Oh, not at all.
Yeah.
Building an optical ground station isn't just pouring a concrete pad and bolting down a parabolic dish. You are dealing with highly sensitive photonics trying to catch a laser beam from a target moving at like 17,000 miles per hour through a highly turbulent atmosphere.
Okay, let's dig into that turbulence, because the note highlights a specific operator, EOS, ticker EOS.ASX. And it says they run stations at Mount Stromlo equipped with adaptive optics.
Right, Mount Stromlo in Australia.
Now, for anyone who tracks aerospace or astronomy, adaptive optics is a familiar term. But why is it a non-negotiable piece of hardware for a commercial data network?
It comes down to wavefront distortion.
Wavefront distortion, okay.
Yeah. When a laser beam travels down from the vacuum of space and hits the Earth's atmosphere, it hits this swirling, chaotic mix of varying temperatures and air densities.
Just normal weather and wind.
Exactly. And the atmosphere refracts and bends the light. If that laser beam hits the ground receiver distorted, the encoded data is corrupted. It's basically packet loss on a massive scale.
So the adaptive optics at Mount Stromlo are actively correcting that atmospheric distortion?
At an incredibly high frequency, yes. The telescope inside the ground station utilizes wavefront sensors to measure exactly how the atmosphere is distorting the incoming light.
Okay, so it measures the blur, basically.
Right. And then it sends that information to a deformable mirror.
A deformable mirror, like it physically changes shape.
It physically changes its shape using microscopic actuators, doing this hundreds or even thousands of times per second.
Wow. Thousands of times a second.
Yes. It perfectly mirrors the atmospheric turbulence to flatten the wavefront of the light back out.
Mm.
Only then can the photonic receiver read the data cleanly.
That is mind-blowing. The mirror is literally rippling in real time to unblur the laser beam.
It's incredible engineering.
It makes perfect sense why the companies manufacturing that specific hardware, like Safran and Cailabs, are positioned as the long-term winners. You can't just slap that kind of engineering together overnight in a garage.
No, the engineering is staggering.
Yeah.
But it also highlights the inherent fragility of the entire architecture. And the source doesn't shy away from this at all.
Right, here's where we have to look at the physical vulnerability of light itself. Because up to now, we are painting a picture of an incredibly advanced, high-throughput network.
Very high tech.
Yeah, we've got lasers, we've got adaptive mirrors deforming thousands of times a second. So what does this all mean? Well, the source introduces a massive caveat, and that caveat is weather.
Good old-fashioned clouds.
Exactly. It states that if the optical mesh fails due to clouds or a lack of stations, the architecture has to fall back to Ka-band RF links, radio frequency.
If we connect this to the bigger picture, redundancy is the foundational rule of any aerospace or telecommunications architecture.
Always have a backup.
Always. Lasers offer unparalleled bandwidth, but they are subject to severe atmospheric attenuation.
Meaning they get blocked easily.
Yes. Specifically, optical wavelengths are incredibly short. We're talking microns. Water droplets in a cloud are physically larger than the wavelength of light, meaning heavy cloud cover completely scatters and blocks the laser beam.
I have to ask the obvious question then. If clouds are the Achilles heel of this multi-billion-dollar infrastructure, why don't we just build all the optical ground stations in the Atacama Desert or the Mojave where it literally never rains? Why deal with the cloud problem at all?
It's a great question, and it's one a lot of people ask. But it comes back to orbital mechanics and latency again.
Okay.
Satellites in low Earth orbit are moving so fast. If a satellite generates critical data over, say, the Atlantic seaboard, and the nearest desert ground station is thousands of miles away, the satellite either has to hold that data until its orbit takes it over a desert,
Which introduces delay.
an unacceptable delay for a lot of use cases, or it has to use the relay network we discussed earlier, bouncing it to other satellites, which again introduces latency.
Right. So to achieve true instantaneous global coverage, you need optical stations everywhere, including cloudy regions like Seattle or London.
Exactly.
And when a thunderstorm rolls over that station in New York or London, the state-of-the-art laser network gets completely shut down.
Which is exactly why the fallback to K-band RF links is absolutely essential. The source lists legacy companies like VSAT and Gilt as the direct beneficiaries of this fallback requirement.
It's just so fascinating that in the middle of this deep dive into next-generation photonics and orbital lasers, we are suddenly talking about legacy radio frequency companies. It sounds like our multi-billion-dollar space lasers get downgraded to an older standard the minute it rains.
Basically, yes. The downgrade in throughput is the accepted cost of absolute reliability. Ka-band radio frequencies have wavelengths measured in millimeters or centimeters.
Much bigger than the laser wavelengths.
Much bigger, so they can easily penetrate the moisture in a storm system that would entirely block an optical link. Now, Ka-band won't give you the multi-gigabit throughput of a clear optical connection, and the RF spectrum is already highly congested, but the waveform pushes through the weather.
So these legacy companies, VS8 and Gilt, they aren't being rendered obsolete by the optical revolution at all. They are being fully integrated into the architecture as the vital fail-safes.
Integrating those RF links is what allows companies to guarantee continuous data flow. If we connect this back to the White House Golden Dome policy for a second.
Right, the secure data policy.
You cannot tell the Defense Department or a major financial institution that their secure data stream is offline just because it's overcast in Washington, D.C.
All right, you'll have your data when the sun comes out. Yeah, that doesn't work.
Exactly. The advanced optical mesh provides the massive capacity when conditions are right, and the legacy RF links ensure the connection never actually drops.
Okay, so let's look at the complete picture we've built so far. We've established a massive 90% deficit in the ground infrastructure. We have a clear roadmap of the corporate winners, moving from near-term relay providers like Kepler to long-term hardware builders like Safran and Cailabs.
Yep, the timeline is clear.
And we even have the realistic RF fallback plan mapped out. It sounds like the perfect setup for an absolute gold rush in investment. But I want to pump the brakes here because the source ends with a reality check that brings this entire analysis back down to earth.
This raises an important question, right? The technological necessity is undeniable, but the actual capital expenditure tells a different story.
Yeah, the note explicitly states, and I'll quote it here, it's not quite sure if CapEx is to the scale of hyperscaler AI buildouts yet to benefit these companies enough.
That's a huge point to make.
Right, because we hear constantly about space being the next great frontier for investment, but the source is comparing the cash flow here directly to the massive AI boom we are currently watching play out. Why is there doubt about the money flowing into optical ground stations?
Well, it's crucial to separate a critical technological bottleneck from actual immediate market capitalization.
Okay, unpack that a bit.
When the source talks about CapEx capital expenditure, it's referring to the real dollars being spent to acquire physical assets right now. Look at the hyperscalers. Companies like Microsoft, Meta, and Amazon.
The giants.
The giants. They're deploying tens of billions of dollars in real cash today to buy GPUs and construct massive AI data centers. That is a unified, highly centralized tidal wave of capital.
And the optical ground infrastructure isn't seeing that kind of unified wave.
Not yet. And the reasons are largely logistical. Building an AI data center is very complex, obviously, but it is ultimately a centralized project in a single jurisdiction. You buy land in Virginia, you build a massive warehouse, you fill it with servers.
You just need lots of power and cooling.
Right. But building a robust optical ground mesh means deploying physical hardware across dozens of different sovereign nations.
The real estate issue you mentioned earlier.
Exactly. You are dealing with fragmented regulatory environments, complex real estate acquisitions, and the sheer physical challenge of laying last-mile fiber optics from remote telescope locations back to the main internet backbone.
So the friction of the physical world is slowing down the deployment of capital.
Exactly, the friction of the physical world. The money is moving, certainly, but the analysis is warning us to temper our expectations regarding timelines.
Just because it's necessary doesn't mean it's fast.
Right. Just because a technology is the defining bottleneck for the entire orbital economy, and just because it is essential for a White House policy objective, doesn't mean the companies building the hardware are instantly swimming in hyperscaler-level cash. The deployment of capital in physical distributed global infrastructure is inherently a slower burn than buying servers for a data center.
That is a vital distinction for anyone analyzing this sector. I mean, the necessity for the hardware is absolute. The 10% deficit proves that.
Undeniably.
But the financial timeline is elongated by the sheer difficulty of building things on Earth.
It demands a highly critical approach from you as an observer or investor. You have to monitor what these hardware and relay companies are actually building and deploying quarter by quarter, rather than just looking at the theoretical total addressable market of a fully functional optical mesh.
So to wrap up our mission for today's deep dive, the core takeaway here for you listening is that the future of the space internet isn't just waiting on better rockets or cheaper satellites. It is currently bottlenecked by the dirt beneath our feet.
The ground segment.
Exactly. The fact that only 10% of Earth's optical ground infrastructure is actually built means the entire orbital laser market is hard-capped.
It's stuck.
And this deficit is directing immediate capital toward relay companies like Kepler and Space Compass as an orbital band-aid, while the long-term structural value goes to hardware manufacturers like Cailabs and Safran, who can actually conquer the complexities of adaptive optics.
And we cannot forget that this entire cutting-edge architecture remains physically vulnerable to atmospheric moisture.
Right, the clouds, which cements legacy RF companies like Viasat and Gilt as the permanent, necessary safety nets for the whole system.
Financially, the need is massive, but we are still waiting to see if the capital expenditure will overcome that logistical friction of global deployment to really match the dizzying heights of the AI boom we're seeing right now.
So the next time you read a headline about a massive new satellite constellation or the commercialization of low Earth orbit, you now have the inside track. The true bottleneck isn't floating in the vacuum of space. look at the ground to see who is actually making all that flying hardware functional.
It completely flips the narrative of the space economy, doesn't it?
It really does.
And I'll leave you with a final thought to mull over, building on the sheer difficulty of what we've discussed today. If our most advanced space communications are currently hard-capped by Earth's weather, and we are struggling to deploy optical ground stations with adaptive mirrors even here, where we have a global supply chain.
And air we can breathe.
Exactly. What happens when we inevitably need to build these optical receiving nodes on the Moon or Mars?
Oh, wow.
You can't just dispatch a local maintenance crew to fix a deformable mirror actuator or, clean a dusty lens millions of miles away.
That really drives the point home. The hardest part of expanding into space might just be figuring out how to keep the data flowing. Thank you so much for joining us on this deep dive.